What the heck?
Hectagon.
Howdy, folks. It's
Wacky Calc Wednesday!
And today we're going to be doing more integrals with the Lambert W function. Yes, I'm going to be presenting two quicker ones, I would say. One of them is a definite integral, and one of them is an indefinite integral. And they're both just sort of interesting things that we can take. Both of them are from the Wikipedia page for the Lambert W function, so I'm simply proving things that appear there for now. One of them is sort of just an even slightly cooler version of the ones we've been doing lately, and by cooler I mean multiplied by some amount, and that's how much cooler it is. And then the second one is a sort of a general form indefinite integral, so let's just get into it. Naturally, I could not do this without my good friend Trusty Cup of Joe. Always there by my side every day, every time, making sure I get my math right. So the integral that we're going to be doing today is sort of a general case. This is not part of the generalization war, this is just me solving the integral. On Wikipedia, it almost looks like this. It's the integral from 0 to pi of w of a times the cotangent, well, I guess we'll do a squared times the cotangent squared of x times the secant squared of x dx. And on the Wikipedia page, a squared is 2, so for the specific integral that's on Wikipedia, it's actually with a equals the square root of 2. And so I'll be solving this in general, and it will actually turn out to be of the form that we evaluated in the Wacky Calc Friday video that I uploaded after a long time. So what we're going to do is we're going to make a simple substitution. We're going to let u equal tangent of x divided by a, which means that du becomes 1 over a times secant squared of x, right? Because that's the derivative of the tangent. Of course, the a isn't part of this, so we have to multiply the a over, and we actually get a times du equals secant squared of dx. So our new integral is going to be w of 1 over u squared, right? Because cotangent squared is 1 over tangent squared, and a squared is 1 over a squared. So we get w of 1 over u squared. I'm sorry, I said this was going to turn into an integral that I did. This is turning into the integral that Papa Flammy did, actually. His holiness, his papal majesty. So we have a times du, right? So multiplied by a times du. And what are the bounds now? So we know that u has to start at 0, right? Which means the tangent has to be... Oh, we have to break this up into two parts, right? Because the tangent and the cotangent are... Yeah, we have to be careful about this. So we have to break this up, actually, into two integrals. So we will be making this same substitution for both of them, we just need to be careful. So we need to break this up into the integral from 0 to pi over 2 of w of, w pi over 2 of a squared times cotangent squared of x times secant squared of x dx, plus the integral from pi over 2 to pi of w of a squared cotangent squared of x secant squared of x dx, because there is a discontinuity at pi over 2 for these functions, so we just have to be careful. So when we plug stuff into here, u is going to be 0 at 0, so that lower bound's not going to change, but at pi over 2, tangent of x is infinitely large, so we'll be going to infinity there. And now we're going to have w of 1 over u squared, and a times du is secant squared of x dx. So the a is going to come out the front, and we have a du right here. Right, and this next one is sort of similar. So tangent of x is, since we're going from pi over 2 to pi, in a sense, we have to go actually from negative infinity up to 0, right? And then we're still going to get w of 1 over u squared times a out the front times du. But now we need to be a little clever. We need to plug in negative u. So for this one, we need to replace u with negative u, right? Which means du is going to get replaced with negative du. which is going to make both of the bounds the negatives of what they were, and this negative sign is going to flip the bounds. So we're making the signs of the bounds negative, and we're flipping them, which now puts them in the same boat, right? But we had to make sure that that was actually going to happen by considering the tangent function over this interval. We can't just assume certain things, because we wouldn't be able to flip them or make certain things negative. So we combine these together, and we get that we have 2 times a times the integral from 0 to infinity of w of 1 over u squared du. And if you've seen Papa Flammy's video on this integral right here, which I will put a card up for, he got this, 2 times the square root of pi, right? So this comes out to 2a times the square root of 2 pi. That's what I meant to say. It was the square root of 2 pi. And so we're just multiplying by 2a. So on the Wikipedia page, the value of a was picked to be the square root of 2. So in that particular instance, so if we call this I of a, right, then on the Wikipedia page they specifically did I of square root of 2, which was the integral from 0 to pi of w of 2 times the cotangent squared of x times the secant squared of x, which comes out to exactly 2 times the square root of 2 times the square root of 2, which is 4 times pi. So we get exactly 4 times the square root of pi for the case where a equals the square root of 2. So this is a very lovely little definite integral, and it's a nice little problem to solve. It's sort of similar to the 2 from before. And now we're just going to quickly take a look at a definite integral, and that will be our Wacky Calc Wednesday for today. I don't have a lot of time this week to film extra long videos because I'm already focusing on a few very large projects for this YouTube channel, that one of which will just be, a couple of which are standalone videos, and then the rest, and a couple of which are series. So please be patient. I'll have a lot of cool math for all of you very soon. So the next thing we're going to do is consider this indefinite integral. The integral of w of x over x dx. And so this is quite easy to solve. It's not too difficult. We just need to make a simple substitution. We want to say that u equals w of x, which tells us what? That tells us that u times e to the u is going to be equal to x, and that tells us that du is going to be w of x over x times 1 plus w of x dx, because that is the derivative of the Lambert W function. So that's something we've seen before, so it shouldn't be too much of a surprise. But we can replace these things with stuff that we know them to be, right? We know that w of x is u, so this is equal to u divided by, we know what x is, it's u times e to the u. And again, we know what w of x is, it's u, so this is 1 plus u dx. And of course we don't want dx to be multiplied by all of these things, we want it to be with the du, so we can replace things. So that simply tells us that dx is going to be equal to u times e to the u times 1 plus u divided by u du, because all we did was take this fraction and multiply it over to the other side so that dx would be on its own. And now we can rewrite the integral and solve and find our final answer. So the integral is now u over u e to the u, right? Because we did these substitutions, u divided by u times e to the u, and now we have to multiply in the differential, times, because we have to replace dx, right? So we multiply by u times e to the u times 1 plus u divided by u du. And we have a bunch of beautiful cancellations. These u's cancel, the u times e to the u cancels with the u times e to the u, and we're left with this very simple integral of 1 plus u du, which is of course nothing other than 1/2 times 1 plus u all squared plus a constant. But we know what u is. U is the Lambert W function. And so of course the final answer is simply 1/2 times 1 plus the w function all squared plus a constant. And that is our final answer. There is a slightly more general integral that I actually, well, actually, let's quickly cover that one too, so that's not too difficult to do. So there's a slightly different integral on the Wikipedia page, which looks like this. It's the integral of w of a times e to the bx dx, right? And essentially what we want to do is we want to just do a u substitution of the thing inside. So we just do u equals a times e to the bx, which tells us that du is going to be equal to a times b times e to the bx dx. But what is what is this thing right here? This is actually b times u, right? Because u is a times e to the bx. And that's a times e to the bx right there, times b. So this is just b times u, which means we can just divide that over, and we get that du divided by b times u is equal to dx, right? Because a times e to the bx is u, and then we're just multiplying by b. Replacing all of those things, we end up with I can pull 1 over b out to the front, right? And we get the integral of w of u divided by u, du. But we just solved this integral. We just found out that it's equal to this right here, which means that this slightly more general integral is actually just equal to this in a special case. So the 1 over 2 times the 1 over b comes out as 1 over 2b. And then we just integrate this, and we get, 1 plus w of u squared. But then we have to replace what we know it to be, right? What we know u to be. So we get 1 plus w of a times e to the bx all squared plus a constant. So we have two lovely little results sort of related to each other, right? These are two definite integrals. So this is the solution to this integral right here, right? This is the solution to this. And in a more general sense, this is the solution to this. So this is sort of this integral in disguise, just with a constant multiplied out the front, namely 1 over b. So if you wanted to multiply by a constant out the front, it actually comes out to this. So it's sort of lovely in that sense. It's a beautiful set of integrals. I hope you enjoyed this little excursion into more of the Lambert W function. The next Wacky Calc Wednesdays will also be related to this function, but they will be much more interesting problems. Very, very specific integrals that appear on the Wikipedia page, which have very, very little explanation around the internet, but I will be providing that explanation to all of you because they are beautiful facts. So stay tuned for the next Wacky Calc Wednesday and enjoy your pandemic. See, I got a lot of water in my brain, but I got no common sense. I got nobody left to me.